Hello, everyone. We are going to be looking at formalizing our idea around testing a claim. So let's move on here. So what we're going to learn is we're going to learn how to state the null and alternative hypothesis for a significance test about the population parameter, interpret a p-value in context, determine whether the results of a study are statistically significant, and make an appropriate conclusion using a significance level, and interpret a type 1 and a type 2 error in context and give a consequence of each. So we're going to learn some definitions regarding the null and alternative hypothesis. My boiler just kicked on, so if you hear this loud roaring, that's what it is. We're going to interpret a p-value, learn what that is. We're going to determine what is statistically significant and making finding a conclusion from that using a significance level, and we're going to talk about type 1 and type 2 errors. So we got to define some things. Now, when making a claim, that claim is going to be associated with a hypothesis. So the claim, if you read that definition, I would take that down in some notes. The claim we're weighing evidence against in a statistical test is called the null hypothesis, the H sub O, or I call it the HO. It's kind of just a joke. So often the null hypothesis is a statement of no difference. So we say that we're assuming that something is true or is what we say it is. For example, when we were talking about that basketball player, we were looking at there was a claim that basketball player made a shooting percentage was 80%. So he would make 80% of his free throws or shots or whatever. I can't remember what the example we just looked at. So let's just say it was a free throw percentage. He would make 80% of his free throws. Well, we're going to take that for what it is. Now, when we tested him, we know that he shot at 64%. So what that makes us do is it makes us wonder, it makes us have an alternative hypothesis. Is he correct, or is his real shooting percentage less than what it looks like? Okay, so we're either going to go. So let's talk about the null hypothesis and an alternative hypothesis. Let's erase some of this first. Okay. So when we're talking about and you should jot that definition down. When we're talking about a null hypothesis, we're talking about the claim that we're finding evidence against. So when we were in the activity that we did, we talked about a basketball player, and that's what we're going to be using kind of here on out. We talked about this basketball player, and this basketball player said, "Hey, I have an 80% free throw percentage. When I shoot my free throws, I make them 80% of the time." That's the null hypothesis. Okay? The symbol there is the H sub O. I like to call it the HO. We'll talk about that. Some funny stuff will come later. So that's the HO, the null hypothesis. And we're going to take some claims against it. And the reason we're going to have claims against it is that player is actually going to shoot. He's going to shoot, so say he shoots 100 free throws and he makes 64 of them. Now we know that his sample proportion, so out of 100 throws, he made 64%. So that proportion is different than what he said it was. It's actually less. So what we're going to claim isn't that what we're going to start to wonder isn't that his actual shooting percentage is 64%, but we're starting to wonder, is it less than 80? Okay, so this is our alternative hypothesis. We watched him shoot. He didn't shoot as well as he said. He shot 64%. Now, we know there's some chance involved there. We know if he shot another 100, it would probably be different than 64%. But what we don't know, and what we're going to try to determine is it going to be consistently less than 80 because his true shooting percentage would be less than 80. Okay, so we have his null hypothesis that he's an 80% free throw shooter, but since he shot less, now we're starting to consider, hey, maybe you're not as good as you say you are. Okay, and we're going to use statistics to help us determine whether or not that we think that that's true. So we have, when we're talking about hypothesis, we can have one-sided alternative hypothesis and two-sided alternative hypothesis. So here's the example of the one-sided. We'll use the null hypothesis of his actual shooting percentage. We'll talk about the basketball being 0.8. Now the one-sided would look like this. It's kind of what we just saw. That one-sided, the alternative hypothesis is that we think it's less than 80. Okay, that's what we're interested in. We're not quite interested in if it's bigger than 80. We don't need to fill his ego. So that would be the one-sided. Now, in some cases, we're interested in a two-sided, where we would be interested in saying, well, we care if it's both below. We care if it's not 80. So we would be looking at an alternative hypothesis of P being greater than 0.80 in this case, or less than 0.80. We would be looking at both sides of that. You can write that inequality however you want to write it, but we'd be looking at both sides of that inequality. Is the true proportion, his true shooting percentage, greater than 80, or is it less than 80? If we cared that much, some cases we do because of the needs of the problem. Some cases we don't. Like in this case, we probably wouldn't be that interested if the shooting percentage was more, because just good for him. But we would care potentially if we were a coach or someone invested in this player, that if it was less, then maybe we'd be less invested, or maybe we'd make different decisions. So, so we're going to. So that's kind of the idea between the one-sided and two-sided alternative hypothesis. So let's check our understanding here. So for each of the following settings, we're going to describe the parameter of interest and state the appropriate hypothesis for a significant level. So if you want to pause and do this, you can pause the video, do this, and then we'll talk about it when you come back, which is now, because if you didn't pause, you're listening to me go right now. So let's read the problem number one. So according to the website Sleep Deprivation, 85% of teens are getting less than 8 hours of sleep a night. Janny wonders whether this result holds in her large high school. So she does a simple random sample of 100 students at the school, how much sleep they get on a typical night. In all, 75 of the responders said less than 8 hours. Okay. So it says, so if we're looking at number one, so first our parameter of interest is this number of, well, actually it's this proportion. It's this proportion of teens getting less than 8 hours. That's the parameter that we're interested in. How many teens in the world, in the United States, whatever, in the web, are actually getting less than 8 hours? Then our hypothesis statements are going to be this. So we are assuming, we're going to test this claim. SleepDeprivation.com said that 85% are getting less than 8 hours of sleep. when Janie did her study, she found that 75 out of 100, so 75%, were getting less than that. So we're starting to wonder, hey, is that percentage that sleepdeprivation.com find actually true, or is it less than that? And that's what we would test. We would test, is it less than what we're seeing? So that's not actually 1 and 2. That's like 1 part A, part B. So we're going to turn that into a B. This is A. So we'll look at number 2 up here. Okay, so number 2, and I might not write the first part. But number 2 says, as part of its 2010 census marketing campaign, the U.S. Census Bureau advertised 10 questions, 10 minutes. It's all it takes. On the census form itself, we read this U.S. Census Bureau estimates that for an average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect that the actual time it takes to complete the form may be longer. So what we're looking at is how long does it take to complete the form? We'd probably be taking an average here, because the mean amount of time it would take to fill out the form. So that would be the parameter of interest, the mean amount of minutes it takes to fill out the form. Our hypothesis is going to be that our HFO is what the Census Bureau, that's the thing that we can go on. The mean amount of time, it's a mu, it's a poor mu, equals about 10 minutes. Our alternative hypothesis, we have reason to suspect that mean may be greater than 10 minutes. And there's our there's our claim, and we have evidence, or we think we have enough evidence to suggest that maybe it's not that, maybe it's greater. Okay, and then we're going to do a test called the significance test later to determine what that is. So let's move on. Okay, p-value. Here's where that significant test comes from. So, here's where we kind of the information for that test is coming from. So the p-value is this probability of assuming H of O is true. So it's a So here's what we have. Let's talk about our basketball player again. So we have our basketball player, right? So he had. And we know that he's saying he's an 80% shooter. Now, we also know that basketball player shot .64. Now, we have to have the question. Now, the question is, can a basketball player who shoots 80% have a rough time and shoot 64%? Is that possible enough just by chance? Was it bad luck that day? Was he in a slump? Is he really an 80% shooter and just didn't do his best that day? We all have bad days. Things go wrong. Is it something that is the probability of this event happening big enough or small enough to make us think that it might be something that his claim might not be true? So we're looking at the probability of getting a .64, assuming that the HO, where P is equal to .80, is true. What's the probability of that? Now, if the probability of getting .64 was really small, if that probability is really small, then we're going to start to wonder if it's so unlikely to occur, maybe his shooting percentages isn't as good as what he says. Now, if it has a decent chance of occurring, so that probability is like 50%. Well, if it's 50%, he just had a bad time. It's such a large probability that, it just could have happened due to chance. And that's what the power of the p-value is. The p-value is that probability. This is that probability of the event occurring, assuming that the null hypothesis is true. So we have a little conditional probability happening here. Okay? So let's interpreting the p-value. This is kind of just what I was saying here. So we're looking at that basketball player. He shot, the alternative hypothesis is 0.80. So if we're looking here, earlier we used a simulation to estimate the probability. So we found that the probability is of 0.64 happening, that shooting percentage, if he's an 80% shooter, was 0.0075. So when we do the math and we calculate that probability, we find that the probability of that is 0.00075. That's really small. Really small. That p-value is really small. So we're starting to wonder now, is that result of shooting less than, is that shooting percentage less than, is that him shooting 80, is shooting less than 80%, is that his true shooting, is that likely, or is that possible? And this is giving some evidence that it might be. Now, we're not going to make a straight up claim and say to that basketball player, you are terrible, you are not an 80% shooter, we have this evidence. But we're just going to we're going to really start to suggest that maybe he is, because we have enough statistically significant information that this probability it's so unlikely to get 64% that you might be lower. So that's kind of the power around this. This p-value is going to allow us to test or to kind of give some measurement on whether a claim is true based on some evidence that we collected. So he makes a claim 80%. He shoots some baskets. And he got 64% of them in. That makes us wonder, hey, are you shooting less than what we think? Is your shooting percentage actually less than what you're claiming it is? And then we calculate the probability that the 64% happening, and that 64% happens to be very low. The chances of that occurring are very low. So then we start to go, since it's so unlikely that you would shoot 64% if you were really an 80% shooter, maybe our alternative hypothesis may be correct. Okay? All right, let's move on. So here we're looking at this example of healthy bones. So we're looking at, it looks like we're looking at the, I'll let you read it real quick, but it looks like we're looking at the amount of calcium, mean amount of calcium in intake for teenagers. So the National Institutes of Health is recommending 1,300 milligrams per day, and we're performing a test to see if it could be less than. So so they ask a sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student. Data analysis reveals that 1,198 milligrams with a standard deviation of 411 milligrams. After checking the conditions were met, researchers performed a significance test and obtained a p-value. So they found the probability. That's the significant test, is obtaining that probability, and obtained a p-value of 0.1404. Okay. So, what would it mean? So, in the setting, the means is equal to 1,300. So, it says that the mean daily calcium intake in the population of teenagers is 1,300 milligrams. If this is true, then teenagers are getting enough calcium on average. Assuming that is true, so this is part B, there is a 0.1404 probability of getting a sample mean of 1,198 milligrams or less just by chance. So 0.14, this is what's going to be crazy for a moment, is not very small. 0.1404, sorry. It's not a very small p-value. okay? We wouldn't consider that small. Before, we said 0.00075 is very small, okay? So that's what we need to consider. Remember, 14% chance of happening is that's pretty big. That's okay. Now, when we're looking at a number like this, we're looking at something that's really close to zero. Okay, getting significant. It's getting closer and closer to zero. It's getting there. So that's what we're looking at. We're really looking at really strong evidence, and we're going to give you a limit here in just a minute. We're going to talk about what that level is. What's the magic number that allows us to accept or reject a null hypothesis? And this is where we come into the significance level. So the significance level is given by the symbol alpha. And we're going to compare our p-value till that alpha. Now, we get to decide what that alpha is. We get to decide what that significance level is. Okay? So most of the time, you're going to see that the magic number being 0.05, 5%. That's the kind of the magic number. You may have heard me mention it in class before. That 5% is the magic number. However, in certain cases, we could set that significant level at 0.01, at 1%. We could set that significant level at 0.10. These are typically the most common significant levels, and all they is kind of some baseline to compare that probability against. Okay, so that's the idea behind a significance level, and we usually choose one of these three. Typically, what you're going to see, at least in this course, is one of those three. Maybe in a different, if you're looking for more precision in a certain field, maybe chemistry or something really that deals with really small things. Maybe you're going to deal with a really small, a much smaller significance level, and I guess it would really depend on the consequences of the study and the consequences of what we're doing. We might want to be really, 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 really sure. But these are still less than 1% is still really, 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 really sure. So it's typically one of these three is the significance level that we're setting. These are benchmarks to compare the p-value to. So let's look at these better batteries. So we have this battery company. It thinks its mean life of the batteries. I'm going to summarize it. You can read it, but I'm going to summarize it. It says the mean life expectancy of these batteries before they die is 30 hours. The company selects 15 new batteries and uses them continuously until they are completely drained. The sample mean of a lifetime, of the battery's lifetime, is 33.9. So they're like, maybe our claim is too low. Maybe these batteries are lasting a little longer. So you can see that in these claims right here. Then they do that test. They do this hypothesis. They do this hypothesis test, the significant tests, and they find that the p-value is 0.0729. Okay? So when they find the probability of the mean being greater than 30 hours, given that the mean is 30 hours, given that the sample, I should use the right symbol. The sample mean being I actually wrote that down wrong. I'm sorry, everybody. What's the probability of the sample mean being of that occurring? This event being 33.9. That's what occurred, given that the population mean is 30. What's the probability of that occurring? Well, they did the significance test, and they found that was 0.0729. Now, we're going to learn how to calculate this next class. We're going to be using some, in the next presentation, we're going to be using some calculator tools, some conditional probability tools. It's really quick. It's nice and easy. We'll get there in the next time. But all that magic happens, and they get a p-value, 0.0729. Now we're being asked to draw some conclusions around that. So if you look at A, which is a significance level of 0.10, now we know that the p-value, which is 7%, just a little over 7%, is less than 10%. The significance level. So because of that, we are going to reject the null hypothesis. Okay? It doesn't mean we accept the alternative hypothesis, but we have enough evidence to reject the original claim. So the idea that these batteries are lasting 30 minutes, we're going to reject it. But we also have convincing evidence that the company's deluxe AAA batteries last longer than 30 hours on average. So we're never going to accept the null hypothesis. We don't the alternative hypothesis. We never say the alternative hypothesis is true. We have strong evidence to suggest that the alternative hypothesis may be true. But what we have is enough evidence to reject the null hypothesis. Okay? So let's look at B, against the significance level of 0.05. Now we know that the p-value, 0.07, so 7%, we know that 7% is greater than 5%. Okay? So because of that, because it is greater, the probability of this occurring is greater than the benchmark, we are going to fail to reject the HO. We're going to fail to reject the null hypothesis, the original claim. So what that means is we do not have enough convincing evidence to suggest that the company's deluxe AA batteries last longer than 30. So you can see kind of that threshold. Now, if you were the company, you would want that. If you were the battery company, you probably would want that significance level to be set at 0.10 because you get to claim your batteries last longer. If you're a consumer reporter, if you're someone who's looking out for the consumer, you might want to use this. It might make a juicy story, or a better story, if those batteries didn't last as long. So you might be writing that. So kind of sometimes statistics comes from whatever angle you're looking at, and the researcher gets to choose their level. Okay, let's move. Almost done here. So when we're rejecting this null hypothesis or failing to reject this null hypothesis, we might not get it right. Remember, we're dealing with probabilities here, not certainties. So we're probably going to get it right most of the time, but sometimes we might not, and that can result in an error. So this little table helps. We have the ability to run into something called a type 1 error, and that's when the null hypothesis was true. So let's talk about the basketball player. Basketball player is shooting 80%, and he shoots 64%. We do our research, and we say, "No, you don't. You don't shoot 80%. We reject your original claim." But say he is. He just had a really bad day that day. Just a freak of nature. He didn't eat enough breakfast. I don't know. But it just didn't result in it. And we said, nope, we reject your original claim. But his original claim was actually true. So we made his day worse. That's committing a type 1 error. Okay. Now a type 2 error is that alternative hypothesis is actually true. Like when we're talking about the population, the secret truth, the truth that we're trying to get to, is like a basketball player, he's not as good as he said he is. He doesn't shoot 80%. But the probabilities didn't work out. Like the probabilities worked out that it wasn't statistically significant. We couldn't reject his hypothesis, so we failed to reject his original claim. But we should have. That's type 2. When we fail to reject that null hypothesis, but that alternative hypothesis ended up being true. So we failed to reject, but we should have. That's called a type 2 error. Okay? So let's look at.
Dun. What the? I won.
Kind of the better battery problem, and we have another check your understanding. So if you want to read through this, pause, do that check your understanding, and then start up the video again. You'll see what the answers are. So we're looking at the battery problem we just looked at. There it is. So describe a type 1 error in this setting. So the type 1 error. So I'm going to draw my little grid here. So we reject, I'm going to use R, reject that hoe. We fail to reject the hoe. And the truth is, the hoe was true. The ha was true. Okay, so this was the type 1. Type 1. And this was type 2. The other boxes are good. Like, we did it right. These are our 2 errors. Type 2, type 1, type 2. So let's think about a type 1. So we rejected the null hypothesis. So we said the battery life is we don't have enough evidence to suggest that the battery life is 30. We know that it could be more in this case. Okay, we know that the batteries could be longer. We have enough. There's enough convincing evidence. We rejected it, but lo and behold, the batteries are 30-hour batteries. That would be the type 1 error. So we rejected the claim. So this one, we rejected the claim that the batteries could be 30, that could last 30 hours, have a lifetime of 30 hours. We rejected that claim. We say, hey, no, it's more, but in real reality, they were 30. Type 2. Type 2. Now we're looking at the type 2 error. Type 2 error says, okay, so we say we have, oh right, we failed to reject that null hypothesis. So we say, yep, we agree, those batteries are, with the original claim, those batteries are 30-hour batteries. They have a lifetime of 30 hours. But they tend to last a little longer. They're better batteries. They are better batteries. So that would be the type 2 error. So which one is more serious? Well, I guess it's up to you to decide, but I guess I would say here, what's the one with the biggest consequence? So if we reject that null hypothesis and that company starts advertising the batteries that last more than 30 hours. They last well beyond that, and that's on the boxes. They slap it on them. They have the commercial. The Energizer Bunny is thump, 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 just thumping away on his drums, and for 30 hours or more, 30 plus hours. We're 30 plus hour batteries, and people started buying them, and they're really detail-oriented people, so they're timing the lifetime on those batteries, and they say, nope, those are actually lasting about 30 hours. Now that I push all these batteries out there, they're 30. That could potentially make consumers angry, especially when the battery hits one of the probability thing. It hits the low end of that curve, and say that battery only lasts like 22 hours or 23 hours. Hits that low end of that spectrum. That consumer may be really mad. They may want their money back. So I would suggest, where in the type 2 error, so I might say, hey, this battery is gonna last 30 hours, and then lo and behold, the batteries are lasting longer. Well, that's extra bucks for the consumer. That's a bonus points for the consumer. No one's gonna be as mad. People aren't gonna return your batteries. Hell, they may even tell people to buy your batteries. So that is significantly less serious because the benefits the benefits to the business and to the consumer are greater. Okay, so that's what we have to consider with these type 1 and type 2 errors. Which one is more or less serious? Okay, so that kind of wraps up this video. I'm not gonna. Thanks for listening, and if you need to go back and check anything out, please do so. The video is going to be up there forever now. So have a good rest of your day, and we'll see you later.